Taylor here. Welcome to today's video where we're walking through question 17. You are given the following information. Tau is a parameter of a distribution. The true value of tau is 2. Alpha hat and beta hat are two uncorrelated estimators for tau. The expected value of alpha hat is 2. The variance of alpha hat is 5. The expected value of beta hat is 3. And the variance of beta hat is 1. Consider the class of estimators of tau, which are of the form w times alpha hat plus 1 minus w times beta hat. Calculate the value of w that results in an estimator with the smallest mean squared error. Start off with what you need to know for this problem is two different ways of looking at what mean squared error is. So first off, the easy way is just in the name itself, the mean squared error. So there is your estimator, so that's denoted theta hat minus the actual denoted theta, so that's error. Square it, and then mean or expected value of that, so that's what mean squared error is. The second form you need to know is that mean squared error, this equation right here, can be rewritten in the form variance plus bias squared. So we're going to do a lot of expanding out squared terms, adding zero in fancy ways, and we're going to be able to get to this equation here. So the way that can be done, first off, let's just expand this out. So we have an expected value of theta hat squared plus negative theta times the negative theta, so we just have an expected theta squared. And then finally, theta hat times negative theta. We do that twice, so minus 2 times the expected value of theta hat times theta. We can then take thetas out of expected values because since we're frequentists, we're saying that whatever the true value is, it just is what it is. It's a non-changing thing. So since it's a constant, we can just pull it out of the expectations. So this theta comes out to the left, and then the expected theta squared is just theta squared. At this point, I want to remind you that the variance equation is just the expected value of x squared minus the expected value of x squared. Also a formula that you should know, although you don't need to know it for this problem. And when we look at this, we can say, well, if I add 0 in a fancy way, I might be able to rewrite things in terms of variance. And so what we're going to do is subtract the expected value of theta squared, and then also add it right back in. So we're just adding 0. But when we do that, we can group these first two terms. So the expected value of theta hat squared, and then minus the expected value of theta hat squared. And that's just variance. So we can replace these two left pieces with the variance of theta hat. And then likewise, what we're left with on the right side is actually just theta hat minus theta quantity squared. Right, so it's that familiar squared squared and then minus 2 times each of those terms. So we can put that back together as the expected value of theta hat minus theta. That whole quantity squared is equivalent to what's left on the right. At this point, if you remember that bias is defined as the expected value of theta hat minus theta, this is just the exact definition of bias. So with that, we can then replace it with bias of theta hat and then square that term, because there's still this square here. And this is how we get to the rewriting of mean squared error as just being the variance of our estimator plus the bias of our estimator squared. I just wanted to walk through this so you know where that's coming from, but really you just need to have this memorized in terms of what you need to know for the exam. So definitely have this equation memorized, along with what variance is, what bias is, as well as the initial what is mean squared error, although that should be easy enough since it's within the name itself. So that's the first thing you need to know for this problem, is this way of writing mean squared error. You also need to know that when you calculate the variance of two random variables, x and y, this is how you can break that up. So the variance of x plus y is just the variance of x plus the variance of y plus 2 times the covariance of x and y. And in this problem, we're told that alpha and beta are parameters of interest, or are estimators of interest, are uncorrelated. So their covariance is 0, so we're going to end up being able to just ignore this term in the problem. Finally, as a bonus, you don't, this is a concept that you don't explicitly need to know to be able to do this problem, but just conceptually it kind of comes up in a few places in the exam, and it is something that comes up in practice in statistics, so it's just good to understand. And I also wanted to create this visual because I feel like conceptually it's something that I struggled with while I was in college. Why would you ever want a bias estimator? Isn't bias bad? So I wanted to share some visuals to show why bias is not the end-all be-all. You can have bias estimators that are still a good thing. So here I'm using the numbers from the problem itself and just assuming it's a normal distribution using their means and variances. But the visual wasn't super obvious what was going on, so I did it again, but where I changed the beta estimator in the problem, instead of it having a variance of 1, it now has a variance of 0.1. And I just did this so that way the visual is way more obvious what's going on. So first, our alpha estimator is this blue curve, and you'll notice that it is centered at 2, which is the true value of tau. So tau is 2, the average alpha estimate is 2, and so it is unbiased. Its bias is 0. However, you notice its variance is really large. So while the long-term value of this estimator is going to be the true value itself, you could get an estimate of 6, something that's just crazy out there. You can compare that against our beta estimator, and in this case, it's centered at 3, so we have a bias of 1. It's typically 1 off the true value. So, bias is bad, we'd prefer to avoid it. However, we're never really off by more than 2. So even though it's biased, it's way better than an unbiased blue estimator, but where we get predictions of 6 or 8. So ideally we want to balance these two things, and you'll hear bias variance trade-off. And that's what this is referring to. So we have these two estimators, and in an attempt to get the best of both worlds, this problem is saying, well, can we do model averaging? Can we take some weighted average of these two estimates? Let's say we take randomly 1 point from the green distribution and 1 point from the blue distribution and average them. If we do that with the optimal to minimize mean squared error weighting, so not 50-50, it ends up being something like 20-80 or something like that, we get the best of both worlds here. So you'll notice the variance is in between the variance of the two distributions, and the mean is in between the two distributions, but we got a nice balance here. So the bias is still non-zero, but it's better than the green distribution, which had a bias of 1. Now it's, let's say, 0.5, so it's a little bias. But we didn't have to sacrifice for the entire variance of that blue distribution. So we're still staying tightly knit, close to 2, and we're balancing both the bias as well as the variance of our estimator. So again, I just wanted to show these visuals to show why just because an estimator is biased does not mean it is useless. And a really good application of this, which also shows up in MAS 1 actually, is lasso regression or ridge regression. So penalized regression methods are examples of biased estimators, but they're obviously useful because of essentially this property that we're seeing in these visuals. Moving on, so now let's actually get into the problem itself. So again, we were asked to minimize the mean squared error using some weighted average of these two estimators. Because of what we're given, you should quickly realize that you want to pull MSE equals variance plus bias squared, and so we just need to calculate both of those terms in terms of W, so we can then take the derivative and find the optimal value. So first off, we are going to have W times our alpha minus 1 minus W times our beta, and take the variance of that estimator. When we do that, we can break everything up here. So when you pull out a constant from a variance, you got to square it. So that's why this W is squared and this 1 minus W is squared. Also, this minus should be a plus sign. I'm just seeing that now. So I apologize for that error. But moving on, so we have W squared and 1 minus W squared multiplied by their corresponding variances. And again, this is going from this to this. This is requiring you to know that since they are uncorrelated, we don't need to account for their covariance. and that's why it's this simple. What we can then do is replace our estimators, so we know our variance of alpha is 5, that's that large variance blue curve, and then multiplying by that w squared. And then likewise, variance of beta is 1 in the problem, and so we have this expanded out 1 minus w squared here. And that just works out to be 6w squared minus 2w plus 0. And I apologize, this 0 also does not need to be there. Next, bias. So just we're going to put a pin in it. We're going to pull this later on. But then calculating bias, we're going to look at the expected value of our estimator, subtract the true value, which is just 2. So again, it's 1 minus w times beta, which is 3, is its long-term expected value, plus our weight to alpha, which is 2. And then subtract off the true value. So you can see here, if we gave 100% of our weight to alpha, it would just be 1 times 2 minus 2 is 0. So we'd have an unbiased estimator. So working through all the math, this just simplifies down to 1 minus w. We can then move on to our MSE calculation and just plug and chug. So we have our variance, which we calculated above, and then we also want to add our bias squared. So we have bias is 1 minus w, and then that quantity needs to be squared. And finally that works out to be 7w squared minus 4w plus 2. At this point we take a derivative and set to 0, so we get 14w minus 4, and w equals 4 over 14. And if we wanted to, we could do our due diligence and take the second derivative to make sure it's a local minimum. But at this point we say w is 0.2857. Scrolling up, that's the amount of weight we're giving our alpha parameter, and that falls in the range of B. So B is our final answer. Really appreciate you sticking to the end, watching my video. If you find these videos helpful and want to get more videos like this, please consider subscribing. Thanks.